Okay, so let me start by telling you what structure preservation is about. So if we think about public key cryptography, then quite often we use mathematical structures of some form. So for instance, a prime order cyclic group, right? And if you multiply two elements, it corresponds to adding together the discrete logarithms of these elements. And this is a very useful mathematical structure. We can build LGML encryption, Peterson commitment, Schnorr proofs, and so forth based on this mathematical structure. And also these components fit together like in a puzzle, right? I mean, you can use LGML encryption, you can do Schnorr proofs about what you have encrypted, and so forth. In pairing-based cryptography, we have a bit of more structure, right? Because now we have two source groups and a target group, and we have a bilinear map, a pairing that maps two source groups elements into the target group. Okay, so in some sense, we have the usual group operations. We can multiply group elements, and that corresponds to adding the discrete logarithms. But we can also pair group elements, and that corresponds to multiplying the discrete logarithms. And this additional mathematical structure then allows us to build more complex schemes, such as non-interactive tripartite key exchange, identity-based encryption, short digital signatures, and non-interactive zero-knowledge proofs, and so forth. So structure preserving cryptography is a philosophy that we should design cryptographic protocols so we preserve as much of the mathematical structure as possible. So in particular, the communication in these schemes should consist of group elements in the source groups. And we should, as far as possible, only use the generic group operations. So we can multiply group elements, we can use the pairing, we can test membership of the groups. But we don't use other operations. Okay? So as far as possible, we just use what we can do within these bilinear groups. So as an example of what we don't do, right, we don't use, for instance, cryptographic hash functions because essentially they're structure destroying, right? They try to mess up the inputs as much as possible so you can't find collisions, and that's not good for our purposes. And the reason we want to preserve the structure as much as possible is because when protocols have been designed with this clean form, it's very easy to put them together and use them as building blocks that you can put together and build more advanced protocols. So let me look a little more into the kind of bilinear groups we're working with. So we have a group generation algorithm. It outputs a description of a couple of source groups and a target group that have prime order P. And then it outputs a pairing, which is this bilinear map that takes two source group elements and outputs a target group element. And it outputs a couple of generators for the source group G and H. There are different types of bilinear groups, okay? And particularly Galbraith, Patterson, and Smart distinguish between three types. So the first type, type 1, is when the two source groups are identical to each other. Type 2 is when they're different from each other, but there is an efficiently computable homomorphism in one direction. So from, say, from G2 to G1, but not the other way around. And finally, we have type 3, where the groups are different, and there are no efficiently computable homomorphisms in either direction between the two source groups. So conceptually, the type 1 setting is a simple one, because we just have one source group that we operate with. Efficiency-wise, the type 3 group is the most efficient one, because it has the smallest group elements. But in this talk, I'm going to focus on the type 2 setting and see what's special about that setting. Okay. So what is the structure preserving signatures? And now we're looking at signatures. What do they look like when they're structure preserving? Well, there's a setup that describes a bilinear group. And then everything has to be group elements in the source groups, okay? So the verification key would be some group elements in the source groups. The messages would be some group elements in the source groups, and the signatures would be some group elements in the source groups. And to verify a signature, we require that you only use these generic operations. So basically, you verify a signature by verifying a set of pairing product equations. So you use the pairing, you use multiplication, that's what you use. And then you'll have to test membership of some of these group elements. Okay, so we already have studied structure-preserving signatures quite a lot, both in the type 1 setting and type 3 setting, so those we understand quite well. And we have some lower bounds of how the efficiency that you can get. So this is something that's special for structure-preserving signatures, and we can actually prove, because they have this mathematical structure, prove lower bounds of how efficient they can be. And we know for type 1 setting and for the type 3 setting that we need to have at least 2 verification equations. You cannot have a structure-preserving signature scheme in these settings with just 1 verification equation. And we also know that they have to have at least 3 group elements in the signature. And now it seems very natural to conjecture, and if you asked me 1 year ago, what would I expect for the type 2 setting, I would say I would expect exactly the same, right? Because it falls somewhere in the middle, right? I mean, the first type 1 setting, we have complete symmetry. We can map elements back and forth between the source groups. Type 3, we have no symmetry whatsoever. We cannot map back and forth. And this one falls in the middle, so you would expect that to be 2 and 3 as well. But it turns out that it's not. The low bounds we find are 1 and 2. So that's very curious. And these bounds here, so these are lower bounds, but they're also upper bounds, okay? So we actually have constructions that match these bounds and are arguably secure in the generic group model. So these are as good lower bounds as we can possibly hope to get. Okay, so this talk here, we complete the picture of what does it look like to have structure-preserving signatures in pairing-based groups. What is the efficiency that you can get in the different types? Okay, I should add here that our lower bound and our constructions hold when the message belongs to the second source group. So in other words, the source group from which you can apply this homomorphism and map into the first source group. Okay? If the message belongs to G1, then interestingly enough, these expected lower bounds of 2 and 3 are actually the ones that apply. So there's another thing that is of interest. So if you look at the efficiency of a signature scheme, okay, so certainly the number of verification equations is one parameter, and signature size is another parameter. But a third parameter is the size of the verification key. Okay? And we know that for these constructions we have in type 1 and type 3 setting, there are constructions that require 2 additional group elements on top of the default generators that we have in the setup. Okay? I put 1 in parentheses because one of the group elements can be a random group element, and you don't need to know the discrete logarithm of that. And then you can include it in the setup and reuse that for many different public verification keys. So what's special in here is that what we show in the type 2 setting, you do need 2 additional group elements, and we can actually prove this lower bound. So this is the first time we prove a lower bound for the size of the verification key. Okay. And we don't know quite what applies in the type 1 and type 3 setting here. Okay. So I'll jump to the constructions first and give you constructions of structure-preserving signatures that satisfy these parameter restrictions that I just presented. Okay, so we're looking at type 2 groups where we have an efficient computable homomorphism from G2 to G1. Okay, and I'll present 2 different structure-preserving signature schemes because depending on applications, you may want different properties from it. Okay, so one scheme will be strongly existentially unforgeable, which means that you cannot forge a signature in a new message, but also you cannot forge a new signature on a message that has already been signed. And the second signature scheme is quite the opposite. It's a randomizable signature scheme. So it's existentially unforgeable, but it's possible to randomize it and make it look like a fresh random signature. And that's useful in many applications, for instance, in anonymous credentials, because when you can randomize it, you can reveal some of the group elements that you have randomized without revealing where this signature came from, what the origin was. So let's start with a strongly unforgeable signature scheme. So the setup is a description of a bilinear group. And the public key, the verification key, consists of two group elements, randomly chosen, and the secret key are the discrete logarithms. And then in order to sign a message in the second source group, we do these computations here. We pick some random value t, and we compute the signature, the two group elements R and S that constitute the signature in the following way. Okay, so it's a randomized scheme. It has to be randomized. One can prove that structure-preserving signatures have to be randomized. You cannot have unique signatures, and it would be able to forge them. Okay, and verification, well, basically you check the membership of the message and the signature that they belong to the second source group, and then you check this pairing product equation. So that's just one pairing product equation we have to check. Okay, so the second construction is a randomizable signature scheme. And here again, the setup is a description of bilinear group. The verification key again consists of two random group elements, and the secret key are the discrete logarithms. And to sign a message in the second source group, well, we can pick some randomness and we compute different type of signature. And to verify it, we check again membership in the second source group and this particular pairing product equation. Okay, so I'm claiming this is a randomizable signature, so let me show how to randomize it. Okay, so get us input a message and a signature, and we'll return a randomized signature. And the way you do that is you take this signature element R, and you multiply that with a random power of the source group generator H. And then if you compute S prime in this particular way and plug it into the equation, you will see that everything works out. So this way we can randomize the signatures. Okay, so let me talk about the efficiency of these structure-preserving signature schemes. Okay, so the signature size is just two group elements in the second source group. Okay, so that's what's particular about these schemes, that we beat the lower bounds that we get from type 1 and type 3 groups. Okay, and other interesting aspect is that it's a unilateral signature in the sense that both of the signature elements are in the second source group. In the type 3 setting, we can prove that you need to have a bilateral signature. There has to be both elements in the source group 1 and in source group 2. And I guess you could say intuitively the reason why both of the group elements can be in the second source group is because we have this map that can be used to map one of them into the first source group. Okay, and then we have the verification key size, which is two group elements in G1, and this is provably minimal, that we need to have at least two group elements. Now, here's what I don't want to claim. I don't want to claim this is more efficient than the type 3 setting, okay? And the reason for that is that if you look at the type 3 setting, then you actually have a shorter representation of the group elements. So even though we only have two group elements and corresponding signatures in the type 3 setting would have three group elements, then our signatures will actually be bigger because the representation of the group elements is bigger, okay? And we've recently received an analysis by Chatterjee and Menezes showing that also, if you look at the verification of structure-preserving signatures, then it's more expensive in the type 2 setting than in type 3 setting. And the reason for that is that it's more expensive to verify membership of the second source group than it is in the type 3 setting. So essentially, you'll have to pay a pairing when you verify membership of these elements in the second source group. Okay. With respect to security, so we proved that these signature schemes are secure in the generic bilinear group model. Of course, it would be nice to prove it under some standard assumptions, but I would expect that's not possible. I don't know whether it is or not, but I'm guessing it's not. Certainly, we know that for type 3 signatures, we cannot prove security under non-interactive assumptions unless we actually use 4 group elements. And I would expect the same applies in the type 2 setting, that instead of having 2 elements, you would need to have 3 elements in order to prove security on a non-interactive assumption. And that we can do, so we can actually tweak the randomizable signature scheme such that it does become secure under a non-interactive assumption by adding a group element to the verification key and a group element to the signature. And then we get this verification equation, so we have this extra element T and this extra verification key element U, and that gives us a signature which is secure under a non-interactive assumption. Okay, let me move to the lower bounds and talk a little about those. So the first case I'll look at is when the message is in the first source group, so that's not the one that I've presented before, okay? And in that case, we can prove that you do actually need to have at least 2 verification equations, okay? So, and we can also prove that we need to have at least 3 group elements in the signature. And the intuition why we need to have at least 3, well, it's basically 2 verification equations plus 1, because we must have randomized structure-preserving signatures. You cannot have uniquely determined structure-preserving signatures. And if you have 2 verification equations, basically you need to have 3 variables to have some randomness to play with. Okay, so this matches the type 1 and the type 3 setting completely. Special case is when the message belongs to the second source group. And in that case, we can show that the verification key must have at least 2 group elements. That we prove essentially by a case analysis and looking at different possibilities for how the signature could look like, what the verification key could look like. And then we also prove that we need to have at least 2 group elements in the signature, essentially because when we have 1 verification equation and we need to have some randomness to play with, then we need to have at least 2 group elements in the signature scheme. Okay, so these 2 theorems show that our constructions are optimal. I should mention here that if you look at one-time signatures, you can actually get smaller signature size. So here it is essential that it is a signature scheme which is secure under, where you can get many signatures and random messages. And to conclude, so we now have the complete picture for all 3 types of bilinear groups, what the size of structure-preserving signatures looks like, namely that we need to have, in the type 2 setting, just 1 verification equation, and the signature size can be just 2 group elements. Thank you.